physics presentation. Sure. I figured he's going to do some question videos just to ask the unanswered type questions regarding some of conventional physics and some of the things that the circumstances that I don't believe adequate explanation has been provided. So 3 questions. Just 3 this time. So the question number 1, let's make that one up. Okay, the lensing argument. So when they do the lensing math for the Eddington experiment, for example, they completely change the circumstance where anything in the normal circumstance in gravity, the gravitational body basically, the gravity goes in all directions from the body. And the idea is the closer some little speck or pixel will be, the more likely it is to intersect one of these lines. These are like only the same kind of lines as you use for magnetism, are the same kind of ideas for gravity. And that your percentage, your ability to be hit by something at a close distance is much higher than your ability to be hit at a further distance. So the same size particle, at a longer distance, the chance of being hit is multiplied by the divergence of the force, essentially. So the force essentially gets weaker as you go further away, taking the same laws that govern magnetism, which basically those laws are, you have these lines to be called lines of intensity. You can make as many as you want for any given location, and then you just obey the rules of magnifying that number by 4 as you double the distance. And so every time you double the distance, you double the intensity. Double the intensity. You proportionally diminish or strengthen, depending on which way you're going, towards or away, the likelihood of getting hit by the force. Now, when they do the math for the Eddington-style experiment for gravitational lensing, that is a photon traveling through gravity, the inverse square law, the 1 over r squared, which creates this doubling, this quadrupling effect. You double the distance, you quadruple the effect, which basically, as I've done it before, means you go from this being the area of intensity to the square of that, which is it's essentially 4 times the size of that square. And if you use if you use the inverse square law to do the gravitational math for lensing, especially solar lensing, it becomes quickly impossible for them to have any effect because they go from a tiny amount of angular deflection, which might be 1.7 arc seconds, to tiny numbers like 0.25 arc seconds, which is in degrees, a millionth of a degree kind of differences they could never detect, just because we don't have instruments that could possibly take a photograph that precise. So the experiment is essentially impossible if you use the inverse square law. And there's, as I can figure, no reason not for the inverse square law to not be used. There's no reason a photon is different than any other thing that would be affected by gravity. If it was a single atom, the inverse square law would apply. Why doesn't the inverse square law apply when it's a single photon? So that's basically the question. Why the change in the mathematical rules? Why is a photon special and somehow it isn't affected by gravity the same way? And let's understand, we have no evidence that it's even affected by gravity, and yet they have assumed a special circumstance where they know somehow it gets affected in this special way. Besides the fact that to even make the experiment possible at all, Einstein had already doubled this number from what it would really be under Newtonian math. So he had already doubled the number by assuming that the photon traveling through gravity actually spends twice as long in the gravity because of time dilation. So even though we know it doesn't spend twice as long in terms of time, because it thinks it is in the gravity twice as long, because it perceives itself to be in the gravity twice as long, that somehow it's actually exposed to the gravity twice as long, and therefore it gets twice as much gravity. So they use 2 tricks. They assume a photon does something nothing else does because it's going the speed of light, therefore it's time dilated, and therefore it is affected by any force twice as much. And they didn't apply the inverse square law, which would apply to any other material body you would calculate the math for. You wouldn't let any other material body be able to escape the inverse square law when it comes to gravity. So, question 1. Question 2. we'll do the slit. Okay, so the traditional double slit experiment or single slit experiment basically is composed of a bar pattern. And the truth is, it shouldn't be a bar pattern. It should, by the mathematics, be a very gradual brightening and darkening of the light. So it should get darker and darker and darker. And it should gradually get light, very light. Gradually darker, darker, and light. So I'm doing a poor job of drawing it, but you get the idea. It's supposed to, in a perfect sine wave, get light and dark. Which looks very different than bars. It should be a very gradual, an intense little line of bright light, and then a very dark line, and the rest should be a very gradual, getting darker and very gradually getting lighter. And it doesn't come out that way at all. The experiments I've seen are done with photons. Now with electrons, it does come out quite gradually. So it comes out similar to what the math would dictate. I've explained a simple explanation for that, which is electrons don't actually hit each other. So when two electrons meet, they bounce off each other's magnetic fields and do not actually hit each other. Where when a photon hits an electron, it does actually encounter the object, move at a specific distance at a specific angle, and then the new photon is released at the new angle. And that's why the pattern is not graduated. It's because the pressure of the electrons is consistent. The frequency of the photons is consistent, and so generally speaking, the width of the slits will essentially decide the separation in size of the bars. You're just magnifying the width of the error in the bar is dictating the size of the bar, essentially, including the fact that the narrower the bars become, the impediment, the more the light diverges, which complicates it. These bars get thicker as the slit gets thinner. But regardless of that fact, it's accounting for the width is essentially the width of the slit inversely proportional. So that's question 2. Why is the math incorrectly describing the pattern in photons? Number 3. The interferometer. So the famous interferometer experiment where you put a beam splitter of some kind, you shoot light, the light reflects into one path, goes through another path, you have a mirror, you reflect the light back, it goes through the mirror coming back this way, and it bounces off the mirror coming back this way, and you combine the two and you get the interferometer. So the thing with interferometer experiment where you put a beam splitter of some kind, simple beam splitter, light to simply reflect into one path, plain piece of glass, another path, hit a piece of plain glass at 45 degree angle, and you create through the mirror coming back this way, and then bounces off the mirror coming back this way. You combine the two and you get but it's fairly close to 50% of the light. The problem with this experiment is that they don't use a simple beam splitter, which would be the simplest. Why don't they use this simple plain piece of glass? You hit a piece of plain piece of glass at a 45 degree angle, and you create 42, probably 25 degrees, and you can adjust it to create your 50-50 without a problem. So this is the simplest beam splitter you can create. Doesn't create any distortion in the beam. The two beams, the one that goes through and the one that reflects, will be the same. The light won't change any. And yet, instead of using that simple beam splitter, they use a complex arrangement where they either put two prisms next to each other with a layer of glue in between that essentially acts as a diffraction gradient in the sense that the glue layer has a bunch of little particles in it, and the little particles create divergence in the light. The light comes in straight, and it leaves in all kinds of little angles. And the other alternative is they use a mirror piece of plain glass. So they take a piece of plain glass, and you put a 50% mirror on the side. And by logic, you can understand that that 50% mirror is going to create little gaps, and those little gaps are going to create divergence in one beam, and the beam that reflects will be straight. It won't be divergent as much because it won't have reflected the light. But clearly, the piece of glass does the job all by itself. Why would you need the silvering layer? So why the complex beam splitter obviously treats one being differently than it treats the other being. The reflected being is going to be different from the being that goes through the glass, quite obviously. By their own theoretical physics, it has to be different. Why would you, if you're trying to create two equal beings, why would you use the mechanism that creates equal beings? Why would you use this silver mirror? Why would you use this complex cube to create an effect that you can create with a simple thing? And how can you be so sure your experiments that are dependent on this interferometer are correct? Your assumptions about what's taking place when there has been no accounting in any of the physics I've seen, many demonstrations of the interferometer, I've seen no attention paid whatsoever to the fact that the thing called a beam splitter can't, in theory, create two equal beings. It's impossible for them to be equal beings. By their own physics, by their own Heisenberg principle, the photons going in between the silvered mirror have to be diffracted. By their own quantum mechanics law, it has to happen. Clearly, the beam that goes through is diverging more than the beam that doesn't. And as I've demonstrated in experiments, by that very principle, I can create the interference rings without having any two beams recombine, by just having one beam bounce off a dirty piece of glass. So those are the three questions that really, in my opinion, not satisfactorily responded to. So compile some other questions, but these are critical elements, critical experiments, fundamental to both Einstein's relativity and the foundations of quantum mechanics. These are foundational experiments with, in my opinion, demonstrably catastrophic flaws in the logic used to defend them. And that's physics presentation. So, here's the some question videos just to ask the unanswered type questions regarding some conventional physics and some of the things that the circumstances that a fully adequate explanation has been provided. So, three questions. Just three this time. So, the question number one, the lensing argument. So, when they do the lensing math, for Eddington experiment, for example, they really change the circumstance where anything in the normal circumstance in gravity, the gravitational body, basically, the gravity goes in all directions of the body. And the idea is the closer some little step like the solar be, the more likely it is to intersect one of these lines. Like, it's the same kind of lines as you use for magnetism are the same kind of ideas for gravity. And that your percentage, your ability to be hit by something at a close distance is much higher than your ability to be hit at a further distance. So the same size particle at a longer distance, the chance of being hit is multiplied by the divergence of the force, essentially. So the force essentially gets weaker as you go further away, taking the same laws that govern magnetism, which basically those laws are, you have these lines to be calling lines of intensity. You make as many as you want for any given location, and then you just obey the rules of magnifying that number by 4 as you double the distance. And so every time you double the distance, you double the intensity. Double the intensity. You proportionally diminish or strengthen, depending on which way you're going, towards or away, the likelihood of getting hit by the force. Now, when they do the math for the Eddington-style experiment for gravitational lensing, that is a photon traveling through gravity, the inverse square law, or 1 over r squared, which creates this doubling, this quadrupling effect. You double the distance, you quadruple the effect, which basically, as I've drawn it before, means you go from this being the area of intensity to the square of that, which is essentially 4 times the size of that square. And if you use if you use the inverse square law to do the gravitational math for lensing, especially solar lensing, it becomes quickly impossible for them to have any effect because they go from a tiny amount of angular deflection, which might be 1.7 arc seconds.